So if we look at how this would work in practice, our unsuspecting user is logging into the big bank's web server, just using normal web traffic. Now he thinks, I forgot my password. So what he does, he clicks on the forgot my password link and enters his email address of joe@bigisp.net. So this is his mail server over here. So the bank's web server needs to send an email containing the password reset link. So it uses the big bank's DNS server. Now let's say I've previously poisoned that by using a cache poisoning attack. So the bank's looking up the ISP's mail server. We're actually going to send a fake entry from the cache. So that basically redirects that DNS lookup to the bad guy's DNS server. So he's basically got control of all the DNS records. So the response that comes back is actually the IP address of bad guy's mail server. So where do you think the bank's mail is going to go? It's going to go via bad guy's mail server, containing the password reset link. And then the email finally arrives at the user, completely unaware that his email has been intercepted by bad guy. Now, of course, you've then got to click on the link before the user does. So one thing you could do is you could not bother actually forwarding him the email, or put a delay in there of, say, an hour or two to give you a chance to go in there and click on the password reset link. And then you've reset his password. So you're on Amazon.com and you're spending all his money on his credit card. So there isn't really a fix for this. It's a fundamental protocol problem. Now Dan actually found you could hack a cache poison a DNS server within 10 seconds using this mechanism. So we worked with various vendors to release some patches to help improve the problem. Basically by improving the randomization of the transaction ID and adding source port randomization. Now, DNS traditionally, the source port of the query that was sent would remain pretty static. So what they decided to do was randomize that as well, so that every DNS query came out from a different source port. So not only did you have to guess the transaction ID, you also had to guess the source port. So basically it increased the amount of randomness, or entropy that you had to use. Now the thing is, it doesn't really matter at the end of the day, because you've got all the time in the world with the Kaminsky exploit to launch this attack. There was a Russian researcher that actually found that even with randomized source ports, you could still implement a cache poisoning attack within about 10 hours. So you could have a botnet out there just slowly attacking DNS servers. You just take your time. And the other problem we found was that with firewalls doing network address translation, that can effectively de-randomize the source port, so that all outgoing DNS queries are coming from the same source port, and then the firewall is mapping it back to the DNS server. So you have to make sure that you're not de-randomizing the source port on your firewall. So the only real way to fix this problem is to use the DNS Security Extensions. Now this isn't new. DNS Sec has been in development for over a decade now, but it's only recently that it's started to gain traction. Now the idea of DNS Sec is it adds cryptographic checksums to the responses. So if someone tries to poison a cache, that entry won't get validated because the checksum doesn't match on the DNS packet, doesn't validate. But it's quite hard to do. Now this is where it gets a bit nerdy, but basically what you do is you take your DNS record, you run it through what they call a secure hash function, and what this does is this generates a hash value, so it's like a unique fingerprint for that particular DNS record. That hash value is then encrypted using a private key. So DNSSEC is all about private-public key cryptography. And what that does, that results in what we call an RRSIG record, which gets attached to the original DNS record. So it's an additional DNS entry. So basically your DNS data will be full of these RRSig records, each one validating DNS records. Now the second part of this is the validation. So we take our DNS record and our RRSig record, we strip off the signature, and then we decrypt it with the public key, and the public key is published in the DNS zone, and that results in a hash value. Now we take the DNS record, run it through the same hash function, that results in another hash value. Those hash values should be the same. If they're the same, it means your data has been validated. If they're different, it means it's not been validated, and then you would choose to ignore it. So you can see there's quite a bit of work to do. And one of the problems with DNSSEC being established is that you need this chain of trust all the way from the root zone on the internet. Because it's all very well me setting up a DNSSEC enabled domain, but I could be the hacker, I could be the bad guy. So someone needs to verify that I am who I say I am. It's no good me setting up an Amazon.com website unless someone above me validates who I am. So for instance, Amazon.com would be done, I'd be verified by the authority that manages .com, in this case VeriSign. Now if you're going through the UK infrastructure, then eventually you'll get to the UK top level domain, that's Nominet. Now the problem is that .com and .co.uk haven't currently been enabled for DNSSEC, so there's an incomplete chain of trust. But this is all being resolved early next year. So what I'm expecting is that next year we'll see a lot more activity with DNSSEC, a lot more people adopting it, because it becomes a lot easier to adopt when the chain of trust is complete, all the way from the root. The root was signed back in July, by the way. So DNSSEC, it's very difficult to do with Microsoft as well. You have to use a command line interface. But there are tools coming out. Some of the IPAM vendors, such as Infoblox, have got a product now where it can automate the configuration and management of DNSSEC. So one of the things you can do is start deploying DNSSEC in your lab, get it up and running, maybe just in VMware. You can even download Bind, the free DNS server, and try it with that. You'll see how difficult it is to set up. And if you're going to do this, then concentrate on the external DNS. I wouldn't worry too much about the internal infrastructure just yet, because none of the clients, like Windows 7 for instance, none of the clients do DNSSEC validation. And if you can't implement DNSSEC, then at least do some monitoring on your DNS servers. So, for instance, the query logs are quite difficult to process because of the size and the quantity of them. So we've got a tool that can help with that. And the sort of things you're looking for are these NX domain type responses, which is basically the responses saying that something doesn't exist because of these non-existent host names. So if you see a large increase in NX domain responses, then you've got an idea that something might be happening. And the thing to remember is that all DNS servers are vulnerable at the moment. There's a lot of fear, uncertainty, and doubt about cache poisoning attacks. There haven't actually been that many in the wild, but hopefully I've given you enough information to realise that it is a weakness at the moment with the protocol. So if you've got any questions or you want to find out a bit more, visit us on our stand 222, where I'll be around, take some questions. And we've also got an article on our website which goes into a lot more detail about this. So if you go to TuscanyNetworks.com, visit the Tech Talk page, you'll see a load of information in there about my speech. So I hope that's been useful. I'm going to close the speech now, but thank you for attending.